Hi, I'm Katie Steckles.
And I'm Peter Rowlett. Hi, Katie. What's today's mathematical object?
So today's object is a taxicab. And right. there are several things going on here. So firstly, there's two reasons why I want to talk about a taxicab. And secondly, taxicab is not a word that I, as an English normal person, would ever use. But it is a way that some people refer to an object which I would call either a cab or a taxi, but not both.
Yeah.
But anyway, a private hire vehicle that you can pay to take you to a place. And it turns out there are two mathematical things relating to taxicabs. So that is the object that I have picked.
Okay.
And I'm wondering if you can guess what the two things are so that you can decide what order we talk about them in.
Yeah, well, I think the two things are a way of doing geometry and anecdote about an old mathematician.
Yes, exactly. Those are the exact two things I'm thinking of.
Of course they are. They're the two mathematical things, right? So
yeah. And I guess given that that's the order you've chosen, let's go with that order. So yes, okay. Taxicab geometry is a type of geometry, and it's kind of a fun. I think it's a really nice example of something that if you do maths at university, you will learn about this, and it kind of sort of changes your way of thinking about geometry in a really nice way. So the idea is the concept of what's called a distance metric. And a distance metric is a way of measuring distance, right? So a way of defining the distance between 2 points. And when you first learn about this in maths, you sort of think, what do you mean, a way of defining the distance between 2 points? It's just the distance between those 2 points. What are you talking about? But it turns out you can actually change the kind of fundamental way that you're defining the word distance. And I guess the usual notion of distance, I'm doing a lot of finger quotes here for anyone who can't see me, but the usual notion of distance is what we would actually call the Euclidean metric or Euclidean distance metric. And it is sort of, it has this definition. It's kind of the distance between the 2 points measured in a straight line. If you're thinking about something that's on a grid, say, for example, a two-dimensional grid to keep things nice and simple, then it's kind of the hypotenuse of the right angle triangle that you make if you draw the 2 points and the horizontal line and the vertical line that sort of connect them together. So it's that sort of diagonal distance. And if the two things are in the same line, like the same height on the grid, then it's just the horizontal distance between them. And if one of them is higher up, then it's this diagonal thing. And this is a very good example of a metric. It's a nice, sensible one that works perfectly well, and it also satisfies the rules that we need a distance metric to satisfy. And again, welcome to maths. This is something you didn't even realize you needed. The definition of a distance has some kind of properties that we require it to have in order for it to be useful as a measure of distance. So in particular, the distance from a point to itself needs to be given by 0. The distance between a point and a point that isn't that point needs to be greater than 0, yep. I guess.
These all seem very reasonable things. Yep.
The distance from point A to point B needs to be the same as the distance from point B to point A, which again feels obvious, but depending on how you're measuring distance may not be true. And then the fourth one is a thing that's sometimes called the triangle inequality, but it's this idea that if you go to a point via another point, it should take you the same amount of time or longer. Like, you can't save time by adding a point to your journey, if that makes sense.
Yeah, so if I go to the bus stop dropping my son at school on the way, I shouldn't end up there quicker than if I'd gone directly to the bus stop.
Yeah, and I guess there we're almost doing it automatically, but we started using a different metric, which is time.
Right.
And in the universe that we live in where you walk at a fixed speed, I guess the distance to get to somewhere and the time it takes you are sort of linearly related. And so the concept of time as a metric would sort of technically also obey this. But if your speed isn't constant, then suddenly that goes out the window, right? If you run from your house to the... Yeah.
Well, I was just thinking exactly that. I'm doing completely the mathematician thing. If I went straight to the bus stop, I would walk quicker, wouldn't I, than walking with my 10-year-old?
True.
So
true.
I might get there in a very different amount of time.
Yeah.
But you're right. I'm assuming I'm an idealized particle that's moving at a constant rate. That's what I meant by walking. What do you want?
This gives us a sort of notion of what it means to not be a valid distance metric. And I guess the time it takes Peter to get somewhere is not a valid distance metric because your speed isn't necessarily constant, depending on whether you're walking or running or whatever. Sure. Another one that I'm a big fan of as a non-example is the cost of train tickets in the UK rail network.
Right. Yeah.
So that this will quite often break the triangle inequality, so that if you buy a ticket from somewhere direct to somewhere, you can actually get a cheaper one by going via somewhere else and buying two separate tickets. You can also, I believe I've seen examples of trains from one place to another costing more than the train coming back the other way for whatever reason, and it absolutely makes no sense, but this is the kind of thing. And I guess these sort of definitions of what we mean by a metric allow us to use it in a way that's consistent and useful and helpful. So Euclidean geometry satisfies all of these things, and there's a bunch of other different metrics that people have defined that have other properties and kind of describe distance in different ways. And I guess the taxicab metric, the taxicab geometry, is a really nice example of this. So it is defined as, if you remember our Euclidean geometry, we had the sort of the right angle triangle that you can make if you draw a line across from one of the points, stop when you get below the other point and go straight up to it. I'm imagining the second one is higher up, and then you get this diagonal line. So the taxicab distance is the distance if you go the other way, if you go along that horizontal line and up the vertical line. And the sort of rough notion of it, and the reason why it's called that, is because if you're in New York City, where all taxicabs reside, or at least all the ones that people call taxicabs rather than taxis or cabs, that's all you can do, right? You can't drive through a city block. You have to go around. So you can only go along the horizontal streets and up the vertical streets. And that's how you get between the two places. And obviously it's slightly incorrect because you can define this distance between any 2 points. So it's not always a case of going across until you get to a junction. Like, there's not a grid that you have to go on, but you can just say the distance across plus the distance up. And this gives you a different way of measuring distance.
And it's called Manhattan distance sometimes because it comes from this grid system, which completely ignores the fact that Manhattan isn't like that. Like, it does have bits of it that are grids, right? And it has older bits that are just a mush of roads. And it also has some diagonal roads as well, I think. And
there's a couple
park
of big...
in the middle, So it's an idealized New York that you're in.
You're just thinking about the bit where it's a grid, but also not even that, because it's literally just horizontal distance plus vertical distance. And as a measure of distance, this obeys all of our nice rules. So it's, the distance from a point to itself is still 0, etc., etc. But it sort of scales differently to how regular distance scales. And it's sort of useful in the sense that if you're a person who's driving a taxi cab in New York, it's useful to know how far away something is, even if you can't go diagonally. But it gives you this alternative definition of distance. As another example, the Chebyshev metric, which is one of my favorite, is the maximum distance in any direction. So whichever out of the X and Y distance is greater, you take that as the distance between the 2 points. And that's another one that is defined in a slightly different way. And I guess one way to sort of see the difference between these things is to think about, and it's fantastic that this is useful, but to think about what we mean by a circle, right? So the concept of a circle. Okay. Like, we know what a circle is. A circle is a shape that's round and it's a circle. But the definition of a circle mathematically is the set of all points that are the same distance away from the centre of the circle. And, when you think about it in that way, and then you suddenly change what you mean by the word distance, then what you actually get is that a circle looks different in different metrics. So the regular Euclidean geometry gives us a round circle, but in the taxicab geometry, the circle is now actually a diamond shape. And it's quite a nice exercise to sort of plot, a bunch of points that are of distance 4 away from a sort of central thing, and see, actually, this is what you get. You get all of these points on this diagonal line that's, I guess, x plus y equals 4. And then all the x, the equivalent things reflected in the 4 quadrants, that's the word, of the thing. So the taxicab distance is a nice way of thinking about distance. I guess, the fact that you need to have multiple definitions of distance is something that probably wouldn't occur to most people. But it's just another one of these great tools that maths has for sort of giving us other ways of thinking about stuff.
I like the idea of a non-round circle, the idea of these boring round circles. Let's have some other things. But that introduces then kind of other concepts, right? The circumference of that circle is going to be a thing, and then circumference and the radius is what's giving you pi. right? So are we defining pi differently in taxicab geometry to regular?
I mean, I guess pi is defined, well, depends how you define defining pi, I guess, but, pi is there for Euclidean circles, but yeah, maybe.
It wouldn't be the same, right?
Yeah,
for every
it's not a shape of constant width
geometry
anymore, so the diameter is a meaningless idea, but maybe the diameter is the maximum.
The distance from the middle is the same each time.
Oh, yeah, so distance is suddenly, yeah. So what's the distance around the outside? You'd have to measure that.
That's what I mean.
Yeah. This is good. So that is one of the two taxicab related things. I'm hoping that's basically a springing off board for anyone who wants to kind of find out more about this. You can definitely look up taxicab metric or Manhattan distance or whatever you want to call it. But the other famous mathematical taxicab is, as you say, from a particular anecdote. And I realise I'm now relating a historical maths anecdote to someone who's got a lot more maths history experience than I have, so I will certainly get this wrong. But I've got the actual quote from Hardy's book, so I can try not to get this wrong. So G.H. Hardy, who was the mathematician who worked with Ramanujan, who came over from India and did lots of wonderful maths things.
Ramanujan had sort of been almost self-taught, or he learned, but he hadn't learned all the things that he comes up with, and he's kind of got this intuitive genius for coming up with mathematical results.
He's kind of he's found some books of maths and used that as a starting point, but basically developed a huge number of different interesting mathematical ideas. And Hardy sort of discovered this through correspondence and invited him to come to England to sort of work with him on developing some of this stuff. And the story goes that Ramanujan was ill in hospital, and Hardy went to visit him. And I'll just read out the quote because it's easier than trying to paraphrase. It says, "I remember once going to see him when he was lying ill at Putney. I had ridden in a taxicab number 1729 and remarked that the number seemed to be rather a dull one, and I hoped that it was not an unfavourable omen. 'No,' he replied, 'it is a very interesting number. It is the smallest number expressible as the sum of two cubes in two different ways.'" Which is both, as you say, a classic bit of Ramanujan, that he's just, he's absolutely ill. He's in bed in hospital, and he's suddenly come out with this interesting fact about a number. And it's become one of these sort of classic math stories of legend, that Ramanujan is this person who can just pull out interesting facts about numbers and obviously lots of useful maths things as well. But it has given us this definition of what is now called a taxicab number. And there's a few different aspects to this. So the number, the statement that Ramanujan made was, it is the smallest number that can be expressed as the sum of two cubes in two different ways. And in particular, 1729 is, I guess it's 10 cubed plus 9 cubed, which is 1728. Sorry, it's 1000 plus 729. And then it's also 1728, which is, I want to say 12 cubed or some 13, something like that, plus 1, which is 1 cubed. And you get these two different sums that add to 1729, but they're both the sum of two cubes. And that's fun. And it allows us to extend this. So the kind of one of the canonical ways of doing this is to say that we have a taxicab number that's a function of n, and the taxicab number is it's the smallest number that can be written as a sum of two cubes in n different ways. So the smallest number that can be written as a sum of two cubes in one way is 2. Because 1 cubed plus 1 cubed is 2. So the taxicab of 1 is 2. Taxicab of 2 is 1729. Taxicab of 3 is 87,539,319. So they get big pretty quickly. And the next one after that is a 13-digit number. And we know up to taxicab of 6 confirmed, which was confirmed in 2008 to be the smallest number with that property. Hardy, working with another mathematician called Wright, did a proof that examples of numbers that can be written as a sum of two cubes in multiple ways exist for all n. So the numbers do exist, and the proof involves a way to construct a set of numbers with that property. So effectively, we know a way to construct a set of numbers with that property, or a number that has this property that it can be written in multiple ways, but not necessarily the smallest one. So we know the first 6 are definitely the smallest ones for that number. And for the other ones, apparently upper bounds are known up to 12. I'm not sure why upper bounds aren't known above that, because surely if we can generate one for any n, then we've got an example which would serve as an upper bound, but there's probably some subtlety there I'm missing. But anyway, we know like a small number of these, and obviously they get massive very, very quickly. So it's one of those interesting, and again I'm doing finger quotes, properties of numbers that you can chase in a direction. And people have kind of modified this and chased it in different directions. So cab taxi numbers, which are an alternative to this, allow you to have one term that's negative, or both terms negative, because if you cube a negative number, you still get a negative number. So, for example, cab taxi of 2, the smallest number that can be written as a sum of 2 positive or negative cubes in 2 different ways, is 91, because that's 3 cubed plus 4 cubed, but it's also 6 cubed plus minus 5 cubed. So you can do that in 2 different ways, and that's why it's the smallest one for that. And then you can also generalize, because obviously there's a few numbers in here that we've fixed in order to get Ramanujan's definition, which is the sum of 2 cubes, 2 different ways, and cubes are all kind of choices that we've made in here. So you can have taxicab of kjn as a 3-input function, where k is the power that you're raising the number to, j is the number of numbers that you want to add together, and n is the number of different ways. So 1729 is taxicab of 322 in this notation. Obviously people have worked out the first few examples of this, but taxicab of 5 to n, so that is the smallest number that can be written as a sum of 2/5 powers in n different ways, is an open problem. So no one has found an example of a number that can be written as a sum of 2/5 powers in n different ways for any n, but no one has managed to prove that a number doesn't exist that has this property. So there's even just a little open problem there on the, if you're into your 5th powers, it's a question you could ask. But yeah.
While you're lying in a hospital bed.
Yeah, presumably it's a good time to just sit there going through, with a calculator, obviously I'm not Ramanujan, but, just go through some 5th powers and see what you get. But yes, it's like one of those sort of classic maths history stories that everyone knows and loves. I believe from the reading that I've done that Ramanujan had kind of heard about this as a property of this number. It's not quite the sort of magical pulling a number fact out of thin air that people present it as being, but because it was previously known that this property of 1729, but presumably Ramanujan, in his broad mathematical interest, had kind of picked this up or read about this somewhere. So it's certainly impressive to have that level of on-hand knowledge to be able to just come out with an interesting fact about a number like that. But I also like the fact that Hardy seems to think that being in a boring cab number is somehow a bad omen. Like, oh God.
Well, that's the thing about this story that I always get is like, why did this even come up? That it's just like, I happened to notice the cab number wasn't interesting.
Well, I sort of...
Why are you telling me that?
Part of me imagines that this is like, he's going to see this guy, he's really not well, like he's worried, and he doesn't want to bring up the subject of anything at all, so he just picks this extremely dry topic. And, he's a mathematician. Yeah, he's a mathematician. He will appreciate the, thinking about numbers and stuff. So it's kind of like a very much equivalent of talking about the weather, I guess, if you're a mathematician. So integers, eh? Like,
Yes.
How about those whole numbers? Yeah. So that is 2 mathematical things to do with a taxi cab.
I did a little bit of quiet searching while you were talking, and a circle in taxicab geometry, pi is equal to 4.
Of course. Yeah. That makes sense, because it's like a diamond and then, yeah.
Yeah. And then there's all sorts of, if you get it on a hexagonal grid or a triangular grid, there are lots of different metrics that you can use, and therefore different values of pi. There's a whole world to explore. Yeah,
I'm not sure how that works, because like the definition of pi as the ratio between the circumference and diameter of a circle is one way to define pi, but it also comes out in lots of other different formulae and, things to do with infinite series and various other things. And I don't know how much of that you have to redefine if you suddenly change the definition of distance, or whether it's just numbers, right? I don't know.
No, I don't know.
But yeah, I guess if you want to call it the circle constant rather than pi, maybe pi is the specific circle constant in the case that we're all used to, and then the circle constant changes depending on the circle, I guess.
Yeah. And yeah, I think if you're mucking about with distance, it's things like when the top of, when the maximum of your function has a pi in it. Well, how are you defining the maximum of this function now that you're doing everything differently? How does a point get put on it just changes everything, right? If you're doing different geometry, I guess.
Yeah.
Cool.
So the thing I've just been reminded of is that in one of the the idea of having different shapes of circles, there's like a whole family of distance metrics that you can define. That in one of the early live streams that we did for a thing called the Finite Group, Matthew Scroggs did a really nice bit about how you define each of these different distance metrics, and he designed a Christmas card with a series of snowmen that were made out of the circles for each of the metrics that started off with diamond-shaped snowmen and went all the way through to circles. And which reminds me, of course, that the Finite Group is a thing that me and Peter are both involved in, and we're currently recording this podcast in the Discord for the Finite Group. So people who are members of our Patreon are actually listening to us record live. If that is something you're interested in, you can go to patreon.com/finite group and find out more about that.
Find out what all the mistakes were that I've edited out.
Absolutely.
You've heard this.
Yep.
Otherwise, we're both online. You can find us lots of places, Blue Sky, Mastodon, places like this. If you search our names, Peter Rowlett, Katie Steckles.
And both Peter and I blog at a website called aperiodical.com, which is where you can find more episodes of this podcast.
And finally, if you want to get in touch, send us any weird geometries that we can explore or interesting number facts. You can email us objects@aperiodical.com. The music is Funk Game Loop by Kevin MacLeod, licensed under Creative Commons. Thank you.